Welcome to Chapter 10, and we're going to be talking about the gases and the gas laws. We will be working problems, the checkpoint problems. So, we had discussed in class that there are four descriptions, variables, that we will be using to describe gases. And those are pressure, volume, the amount, and temperature. So pressure is P, volume, N is the moles, and T is temperature. And we also talked about how you have the gas constant, which is R. And if you look at your periodic table, you'll see that's 0.08206 liters atmosphere over mole Kelvin. And the reason why I bring this up is because these are the units that you want your variables to be in. So pressure, you want to be in atmosphere. Volume, you want to be in liter. The amount is moles here. And then we have temperature in K for Kelvin. So a lot of times you're going to be given some kind of degrees Celsius. To convert that to Kelvin, you need to add 273 K for Kelvin. So you want to do that, 273, and then that's going to give you your temperature in Kelvin. So for example, 0 degrees Celsius would be 273 Kelvin. The other conversion that you need to be aware of is pressure. So we also said 760 millimeters of mercury equal 1 atmosphere of pressure, because you want your pressure to be in 1 atmosphere. Also 760 torr equals 1 atmosphere. So that might be a conversion you need to do from time to time to solve these problems in order to get your pressure in atmosphere. Volume, just make sure it's in liters. And if you're given grams of a substance, then you want to use the molar mass based on that molecular formula to grams to moles to get into N for moles. So those are the conversion factors you need to do. If you look at the first section, you'll see defining pressure and talking about pressure in the units. And then there's the checkpoint problems in section 10.1, but I'm not going to have you do those. I've basically said here what I need you to be able to do in terms of unit conversions. So we're going to go straight into section 10.2, which is the gas laws. Okay, so section 10.2, gas laws. And I expect you to do your reading, and you'll see that Boyle's shows the volume and pressure, and that volume is inversely proportional to pressure. So that means if you increase the pressure, you're decreasing the volume. If you increase your volume, you're decreasing the pressure. And what you could do is you could solve for this and set it equal to a constant. And so if you did that, you would have to do PV equals K, where K is a constant number. And then if you do that, then you can say, let's make these all condition 1, and then you can solve it again for PV for condition 2. And you can make that equal to the same constant. And then when you do that, you can do P1 V1 equals P2 V2. And then if you have constant temperature and amounts, so mole, then you can use this equation. So if you need to solve for V2, then you would isolate that variable and you go P1 divided by P2 times V1 equals P2. And so you want to be able to do that. you also see um, in your reading that there's Charles's law. And Charles's law does the volume is proportional to temperature. And so these are, if you increase volume, you increase temperature for a gas. If you decrease your volume, you're decreasing your temperature, or you decrease temperature, you're decreasing volume. So these are directly proportional. So this is called a direct proportional. This is called an inverse, a proportional. Now, when you set that equal to a constant, so if you did V1 over T1 equals a constant, and you did this for V2 over T2 equals a constant, and you set these constants equal to each other, you would have a new equation, V1 over T1 equals V2 over T2. And then let's say you wanted to solve for a second condition of changing temperature, and this would be a constant moles in and constant pressure P, because those are the other two of the four variables that aren't there. If you had to isolate that variable, you would want to solve for that variable where you multiply both sides by T2, that cancels out. Now you got T2 over T1 times V1 equals V2, and you could, in that case, solve for V2. If you wanted to solve for T2, I don't know if that's what we wanted to do at first, you would just have to say T2 equals V2 over V1 times T1. So you need to get used to where you can write these equations and solve for the different variables with constant temperatures or constant pressures, depending on what the problem's asking. The other one is Avogadro's law. Sometimes I call this avocado, right? Avogadro's law. And this is volume is directly proportional to the amount, the moles. And so this is a direct proportional, which means V1 over N1 equals a constant. And then you could do V2 over N2 equals a constant. And then if you set these constants equal to each other, you would have a new relationship, V1 over N1 equals V2 over N2. And so at constant, what are the two variables missing? Pressure and temperature. You could solve for a changing condition. So if you want to solve for V2, then you would isolate V2. You'd say V2 equals N2 over N1 times V1. You don't have to do these in parentheses like this, but I just like to kind of keep those together because those units will cancel out, leaving you with the units for volume, and the units for volume is going to be liters, right? Because we talked about the R constant. Now, if you have trouble memorizing all this or you bring them all together, I find that the ideal gas equation is helpful. But we're going to do that next because I'm going to work some checkpoint problems first. So what if we bring all of these together before we go on to work some problems? So we said we had pressure, volume, moles, and temperature. And so we can bring all these together. So we have PV equals nRT. So, and R is the gas constant. So we've been talking about constant. So if we solve for R, we would divide both by N and T by N and T. Okay, so they cancel out. So if you rewrite this, you have the gas constant equals PV over NT. R is your gas constant. Now what you can do is you can make all these 1, 1, 1. So I went ahead and showed you this is the ideal, this is your ideal gas law right here. PV equals nRT. We call it perv nert. Okay, perv nert. And so this is how I memorize everything. So you can solve for R, and then you can set these equal to each other. So using perv nert, if you set these equal to each other, Then you have P1 V1 over N1 T1. Then you would say equals a second condition, P2 V2 over N2 T2. And what's going to happen is when you read in these problems, you might be just changing PV and T, but keep an N constant. So then you could just exit out N. And then if you're changing some variables or you're wanting to solve for like T2, then you could then go T2 equals, and you bring this up here, right? And then you would have to isolate the T2. So it would be P2 divided by P1, and then you'd have V2 divided by V1, and then you'd multiply the T1 up here. So you could actually have all these different conditions and solve for a final temperature, T2, which is a final temperature, depending on what the problem is asking you. So this is how you need to be able to set these conditions equal to each other. You can just X out any kind of condition that is being held constant, and then you can rearrange your equation, and then we're going to do a thing called plug and chug. So let's look at some checkpoint problems. Okay, so the first checkpoint problem we have is 10.2.1, and okay, so we have conditions, and I'll put the P1s in blue. So we have P1 is 1.50 atmosphere, and V1 is 37.3 milliliters. And then we have P2, so we'll go over here, P2, I like to keep my pressures on the same line, 1.18 atmospheres, and it wants you to calculate V2. And it says assume N and T are constant. Okay, so what I like to do, because I like to memorize just one formula, I do PV equals nRT. There's my perv nerd. I'm going to solve for R, which is the gas constant. So I'm going to go PV equals R divided by NT. So I'm going to start here. Now, notice N and T are constant. So I'm going to mark out N and I'm going to mark out T. And then I'm going to rewrite P1 V1 equals, and I'm going to replace the gas constant here with the P2 V2. And so this is my equation that I'm going to be using. Notice I have to solve for V2. So I have to isolate V2. So I'm going to go V2 equals P1 divided by P2 times V1. So this is the formula that's going to give me the answer. Now I plug and chug. I have defined my variables up here. So now I'm going to just go V2 equals P1 is 1.50 atmospheres, and P2 is 1.18 atmospheres, and then V1 is 37.3 milliliters. And the answer can be in milliliters, and that's fine because we're not using the actual R, which uses liters. So if you do that in your calculator, 1.5 divided by 1.18 times 37.3, you should get 47.4 milliliters, and that corresponds to the answer E. All right, so let's go to 10.22. Well, a lot of these just take practice. So we have T1 equals 21.5 degrees Celsius, V1 equals 50.0 milliliters, and T2 equals 316 degrees Celsius, and it wants you to calculate V2. And it says N and P are constant. So once again, the only thing I have memorized is my perv nerd, PV equals nRT. I'm going to solve for R, because that's the gas constant, PV divided by NT. And now I'm going to mark out N and P because they're constant, N and P. And I'm going to rewrite this as V over T. And I'm going to put my ones there. And then I'm going to say equals V2 over T2. And so I'm going to make these my blue. I'll make these my red. And so, did something, it says T. T1, T1, and V. Okay, yeah, I see. I'm sorry, I just got confused there. Okay, so I need to solve for V2. So I need to solve for V2. So I want to rewrite this equation where V2 is isolated. And so that's going to mean T2 divided by T1 times V1. And so now I'm going to plug and chug. V2 equals T2, which is 300. Ooh, I can't do that. I've got to convert that to Kelvin. That does matter. So what's 316 degrees Celsius plus 273 Kelvin? That is 589 Kelvin. Oh, well, yeah. And then what about T1? 21.5 is 294.5 Kelvin. All right, so V2 equals 589 Kelvin divided by 294.5 Kelvin. And then my volume, V1, is 50.0 milliliters. And if you do the math on that, so you take 589 divided by 294.5 times 50, you get V2 equals 100 milliliters. And that is answer A. Okay, so we can go on to 10.23. At what temperature will a gas occupy 100 liters? So we're talking a volume. So that's a V2 because if it's originally occupies, so we're looking at V1 must occupy 76.1 liters, and T1 temperature is 89.5 degrees Celsius. Let's go ahead and get that 89.5 degrees Celsius in our Kelvin. So if you add 273 Kelvin onto that, you're going to get 362.5 Kelvin for your T1. And we need to solve for T2. So we do our equation. Like I said, perv nerd, PV equals nRT. We're going to solve for R. So PV divided by NT equals R. And we're going to hold N constant, and we're going to hold pressure constant. It says assume constant pressure. You can go ahead and assume constant N as well. And now we're going to rewrite this as V1 over T1 equals V2 over T2. We want to solve for T2 here. So now I'm going to isolate that variable T2 equals, we do that, then I've got to say equals V2 divided by V1 times T1. And that isolates my variable. And then I can do this thing which we call plug and chug. V2 is 100 liters. V1 is 76.1 liter. And you multiply that by T1, 362.5 Kelvin. And that should give you a T2 of 476.3 Kelvin, But if you look at the answers, you see they're all degrees Celsius. So now you have to say T2 is 476.3 Kelvin minus 273 Kelvin to give you degrees Celsius. And I get a 203.3 degrees Celsius. And that is answer C. Let's do problem 10.2.4. What volume of ammonia, NH3, will be produced, so we want the volume, produced when 180 milliliters of hydrogen react with 60 milliliters of nitrogen, according to the following equation: 3H gas, 3 moles, plus 1 mole of nitrogen gas goes to 2 moles of ammonia gas. And it says assume temperature and pressure are constant. Well, you know that you're going to do PV equals nRT because those are our variables. And you have to see that initially, let's talk about initially, which is V1, which is initial. You have 180 milliliters of hydrogen and you have 60.0 milliliters of nitrogen. And so these are our volumes. And so if you add that volume together, you initially at volume 1, you have 240 milliliters. And how many moles do you have? In 1, you have 3 moles of hydrogen plus 1 mole of nitrogen. You have 4 moles. Now, it asks for what's the volume of the ammonia, the product. And so this is going to be V2, and we're going to solve for that. But how many moles do you have? You have 2 moles. So this is that Avogadro's relationship. So here we have PV equals nRT. Let's solve for R divided by NT. And then we get to hold temperature constant and pressure constant. So now we have V1 over N1 equals V2 over N2. And we're solving for V2. And so we've got to isolate V2. So V2 equals N2 over N1 times V1. Okay, so we're going to do that. Let's make sure we're on the same page here for N1. I'll make that color. And then V1. So now we want to plug and chug. So we have V1 is 240 milliliters. And we have N1 is 4 mole. And then we have N2 is 2 mole. And you see where I switched that, and you've got to be careful because N2 is on top, isn't it? So we need 2 moles on top, N2, and then on bottom we're going to have 4 moles because you will get the wrong answer, and sure enough, it'll be there. So if you take 2 divided by 4 and multiply that by 240, you get V2 equals 120 milliliters. And you see that that is option A. The ideal gas equation is perv nert, PV equals nRT. And usually you don't have one condition changing with the other condition. This is called the ideal gas equation. And what that means is this is a gas behaves ideally, which means there's no interaction with each other. And that means there's no intermolecular forces. So there's no intermolecular forces. You also learn that there's a thing called STP. This is standard temperature and pressure. and you want to memorize that. It's at 1 atmosphere, and it's at 0 degrees Celsius, which is 273 Kelvin. And what is the volume at STP? Well, you can solve for that. PV equals nRT. Solve for volume. V equals nRT divided by P. And then plug in for 1 mole of gas. So N equals 1 mole of gas. R is your gas constant. 0.08206 liters atmosphere mole Kelvin. Temperature now is 273 Kelvin. And pressure is 1 atmosphere. And if you solve that, volume equals 1 mole times 0.08206 liters atmosphere mole Kelvin times 273 Kelvin divided by 1 atmosphere. The volume should be 22.4 liters. Now, the reason why that's important, because you're going to be able, anytime you see STP in an equation, you can use a conversion factor. And that conversion factor is 1 mole of gas, any gas, occupies 22.4 liters. So that relates the volume, so you can do dimensional analysis. I will also say, what is the size of a 22.4 liters? It's the size of a basketball. So it's a basketball full of gas. And that's 1 mole. So 1 mole of ideal gas at 0 degrees Celsius and 1 atmosphere, that's what we're at, it's going to occupy the size volume of a basketball. Okay, the other application you need for ideal gas law is the molar mass. So there is the other equation that you need to know, and I call it dirty P. So it's the molar mass, see the squiggly? That's molar mass, which is grams per mole, so we can identify an unknown gas. So you're going to be able to do that equation, and I just go dirty P, dRT over P. Any other equations I'll give to you, and I will give this to you also. So you need to memorize STP, you need to know what units based on R, and you need to know perv, nert. But as for this, I will give you the molar mass equation, just to minimize how much you have to memorize. All right, let's go to the checkpoint problems in 10.3 and work those problems. So 10.3.1, calculate the volume occupied by 8.75 moles of an ideal gas at STP. So you could go and solve it with PV equals nRT, and then you'd have to put temperature equals 273 Kelvin. You have the R constant, P equals 1 atmosphere, and then N would equal 8.75 moles, and then R equals 0.08206 liters atmosphere mole Kelvin. And you can do that. Or you could just say 8.75 mole of gas, dimensional analysis, and for 1 mole of gas, we have 22.4 liters of gas. And then if you get your calculator out, you will see that that works out to be 196.1 liter, and that is A. And the mole of gas cancels out. Okay, let's do 10.3.2. Calculate the pressure exerted by 10.2 moles. Now this one you're not going to have a choice because it's not STP. You can only do what I just did at STP. All right, so let's list this. We have 10.2 mole, which equals N. We're defining our variable, of an ideal gas volume equals 7.5 liters, and the vessel is at 150 degrees Celsius. We have to convert that degrees Celsius to Kelvin, so add 273 Kelvin, so your temperature now is going to be 423 Kelvin. Now you want to do your ideal gas law, which is PV equals nRT. You want to isolate the pressure, so P equals nRT divided by V, and then you want to plug and chug. P equals 10.2 mole, and for full credit you need to show your units. R is 0.08206 liters atmosphere mole Kelvin, and I want to see these units written with the numbers. That is on your periodic table, so you don't have to memorize it. Temperature is 423 Kelvin, and then you divide by the volume, which is 7.5 liters. Notice that the moles cancel out, Kelvin cancels out, liters cancel out, and you're left with atmosphere. And what is the units for atmosphere? For pressure is atmosphere. And when you do that, do you get, from your calculator, do you get P equals 47.2 atmosphere? And so E is the answer, 47 atmosphere. Okay, so let's do 10.3.3. Determine the density of a gas with a molar mass of 146.07 grams per mole at 1 atmosphere and temperature of 100 degrees Celsius. Once again, I'm going to go ahead and add 273 Kelvin to make that 373 Kelvin. Now, like I said, I'm going to give you this equation where M equals dRT over P. I call it my dirty P. And we're going to solve for density. So we're going to solve for that little d. And so we have M times P equals D, and this is all over RT. And now you want to plug and chug. You have 146.07 grams per mole. The pressure is 1.0 atmospheres. The R is 0.08206 liters atmosphere mole Kelvin, and the temperature is 373 Kelvin, and this equals your density. And you see that atmospheres cancel out, Kelvin cancels out, mole cancels out, and you're given your units are grams per liter, and that is a unit for density. And when you do the math on that, do you get 4.77 grams per liter? And that answer is B. All right, and let's do 10.34. Determine the molar mass of a gas that has a density of 1.963 grams per liter at 1.00 atmosphere and a temperature of 100 degrees Celsius. Once again, I'm just going to go ahead and add 273 Kelvin, so that'll be 373 Kelvin for my temperature. Now we have M equals dirty P. Now you will have to solve for M. We have M here. So we go density 1.963 grams per liter. The R is 0.08206 liters atmosphere mole Kelvin. Temperature is 373 Kelvin. And then you divide by the 1.00 atmosphere. Atmospheres cancel out, Kelvin cancels out, liters cancel out, and we're left with grams per mole. Is that the correct unit? So it kind of gives you a layer of checking. And yes, that is the correct unit. And when you put this in your calculator, you get 60.08. And you could actually probably assign that with elements or a compound if you were given those choices in your multiple choice questions on an exam. All right, now we're going to go on to section 10.4. So now we're going to deal with reactions, and this section is going to talk about stoichiometry. So we're going to talk about how to figure out volumes from amounts if you're given a reaction. So let's go on to your checkpoint problems. 10.4.1. Determine the volume of chlorine gas at STP. Whenever I see STP, I'm thinking 22.4 moles of a gas, or that's so wrong. Okay, 22.4 liters equals 1 mole of gas. Okay, that will react with 1.00 mole of sodium solid to produce sodium chloride according to the equation. So let's look at the equation because we're going to need those coefficients in the balanced equation. So you got sodium and chlorine gas. It's kind of interesting how sodium will catch fire, chlorine gas will kill you. But when you combine them, you make sodium chloride, which is table salt, which is a different property. Okay, the question is they want to know the volume of chlorine gas at STP that will react with 1 mole, 1.0 mole of sodium to produce this. Okay, well, what's our given here? 1.00 mole of sodium. And for 2 moles of sodium, what product do they want to know? Chlorine. So we got to do the mole to mole bridge. We have 1 mole of chlorine. So now we got moles of chlorine, and it wants the volume, and we're in moles. So then we can say for 1 mole of chlorine gas, we have 22.4 liters of chlorine gas. And you can do that because you're at STP. Otherwise, and we'll see that in the future, where we have to actually do something different. We have to use pervnert. You see how moles of sodium cancel out and moles of chlorine cancel out, and we're given liters of chlorine gas. And so you take 1 divided by 2 times 22.4, and I get 11.2 liters of chlorine gas. And that is answer D. Okay, let's do 10.42. Determine the mass of sodium azide. This is what's in your airbags required for an airbag to produce 100 liters of nitrogen gas. That's what actually happens at 85 degrees Celsius and 1.0 atmosphere, according to the equation. So sodium azide, 2 moles, is going to react to make 2 moles of sodium solid plus 3 moles of nitrogen gas. And the question is asking for the mass. So we want grams of sodium. So we want to know how many grams we need of sodium azide, and we're starting with the volume, 1 liter, 100 liters of nitrogen. So we're starting with 100 liters of nitrogen gas, and we are also given conditions. So that's volume, and we're given temperature. So here we have 85 degrees. Let's go ahead and add 273, make that Kelvin. Because you get 358 Kelvin. And so that's our temperature. We have volume, pressure, We have pressure is 1.00 atmospheres. So what all do we need? PV equals nRT. We have P. We have volume. We have temperature. And we need to figure out moles. Because if we can solve for moles, so N equals PV over RT. So if we solve for moles, which is N of nitrogen gas, then we can use dimensional analysis to go from 3 moles of nitrogen gas equals 2 moles of sodium azide, and then for 1 mole of sodium azide, we have, what's the molar mass? So if you look at the periodic table, you had 23 for sodium, you got 3 nitrogens, 65.03 grams of sodium, then we can get the mass. So let's solve for N. So N equals 1.00 atmosphere times the volume, 100 liters, divide by R on your periodic table, 0.08206 liters atmosphere mole Kelvin, times the temperature, 358 Kelvin. And then we just make sure our units cancel out. Atmospheres, liters, Kelvin. And that gives us moles. And so if you do that math, do you get N equals 3.40 mole? Okay, and that is of nitrogen gas. So now we can do some dimensional analysis. So we're going to do 3.40 mole of nitrogen gas, and for 3 mole of nitrogen gas, we have 2 mole of sodium azide. Okay, and then for 1 mole of sodium azide, we have 65.03 grams of sodium azide. And so when we do 3.4 times 2 divided by 3 times 65.03, do you get 147.4 grams of sodium azide? And that is, well, you might have gotten a rounding, I might have gotten a rounding error. So the answer is 148 grams. So it's probably in my molar mass there, in my rounding. So the answer is B, but that's how you do it. So now we're going to go on to Dalton's partial pressures. So we've been talking about a single gas in a container. And now we're going to talk about a mixture of gas. So what if you have more than one gas? So when you have a mixture of gases, they act independently. So you can just add them all up. Okay, so this is a new formula. You have to have that memorized. Dalton's law of partial pressures. And that means the pressure total is the summation of each of the pressures. So if you have a container with a pressure of nitrogen gas at 4.48 atmosphere, and you add an oxygen gas, which will be treated independently, and it also has 4.48 atmosphere, the total pressure of the system would be 4.48 plus 4.48 atmospheres. So you take the pressure of oxygen plus the pressure of nitrogen, and you can just total these up. So that would end up being the total pressure of the system is 8.96 atmosphere. So there's also a thing called mole fraction. And you have to know this. So a mole fraction is a fraction. It's the moles of the little one, so the part over the whole. And you need to think about that anytime you do a fraction. So whatever the moles of the part over the moles of the total. Total is always going to be the whole. Total is the whole. And that is a mole fraction. And mole fraction is now represented as xi. And whatever one you're talking about is ni. And you can do the same thing with the fraction with the pressure, partial pressure versus total pressure. And then you can manipulate that equation to say the mole fraction times your total moles will equal the moles of the individual. You're just multiplying that through. And same thing here, you can say the mole fraction times the total can give you the partial pressure of that individual element. So you'll want to be able to apply these formulas. And they all basically come out of Dalton's partial pressure, which is the summation of each one of these individual pressures. All right, so let's work some of those problems, checkpoint problems. We'll do 2 problems to show how we can solve problems using this. So let's do 10.5.1. What is the partial pressure of helium in a 5.00 liter vessel? Okay, so it's a volume at 25.0 degrees Celsius and contains 0.0410 mole of helium. It has 0.121 mole of neon, and it has 0.0922 mole of argon. So we have 3 gases in that mixture, and the first thing I do is I total up all of my moles. So if you add all of these together, you should get in total of moles should be 0.2542. And let me just double check that. So I have a different number here. Let me check it again. 0.0410 plus 0.12121 plus 0.0922. I get 25. Okay, so that is the total moles. So you have the total moles, and what you want to do is solve PV equals nRT, and you want to solve for the pressure. So pressure equals N, and this is total, times RT over V, because it wants to know the partial pressure of helium. So the partial pressure of helium is going to be the mole fraction of helium times the total pressure is the pressure of helium. So we are going to now solve for the total pressure here using PV equals nRT, because we have the total number of moles. And what's our mole fraction? Mole fraction here would be 0.0410 mole of helium over our total moles, 0.2542. So that mole fraction is going to be 0.161, and let me double check that one as well. 0.0410 divided by 0.2542. So that's our mole fraction. So we have this, and we're solving for this, but now we need to find PT, and we're going to do that using Avogadro's, or the ideal gas equation. So PT is 0.2542 mole R 0.08206 liters atmosphere mole Kelvin. And the temperature here, we've got to convert 25 to add 273 Kelvin, and that's a 298 Kelvin. So we put 298 Kelvin in there, and then we're going to divide by the volume of the vessel, which is 5.00 liters. I like to make sure that my units cancel out, Kelvin and Kelvin, mole and mole. We're left with atmosphere, and so the pressure total, did you get 1.243 atmospheres? And now we can solve. We can say, okay, we have 0.161, and that's a dimensionless, there's no units, times 1.243 atmosphere, and then that will equal what we were looking for, the partial pressure of helium. And so when you multiply that, let's see, 0.161 times 1.243, I get the partial pressure of helium is 0.200 atmospheres. And when I look to see what I have as options, I have 0.201 atmospheres. So that must be my rounding, and E is your answer. Okay, let's do the 10.5.2. What is the mole fraction? So mole fraction, if you remember, is X of CO2. So instead of I, we'll do CO2. So mole fraction of CO2 is the moles of CO2 N of CO2 over the total moles. And we have a mixture of 0.756 mole of nitrogen, 0.189 mole of oxygen, and 0.0132 mole of carbon dioxide. So let's add all these up to get our N total. So when you add the N total together, did you get 0.9582 moles? And we have our mole fraction, or our small part here. This is N of CO2. So now we can do 0.0132 mole of CO2 divided by our N total, 0.9582 mole, which is our total, and that's going to give us a mole fraction of 0.0138, and that answer is B. Now that gets us through all the calculations you need to be able to do for Chapter 10. Now you do have 2 sections left, so we're just going to talk about the theories on those, and we'll work a checkpoint problem. So in section 10.7, we're talking about deviation from ideal gases behavior. And these are called real gases. And we don't really talk about these unless you're like a chemical engineer and you have to deal with real gases. But real gases do have intermolecular forces. Okay? And so you can read this section and see how there's an equation and how these intermolecular forces will have an effect on the behavior of the ideal gas equation. So if you look at the PV equals nRT equation, you see that there's this portion here that, and if you were a chemical engineer, you would have to spend some time on this. But it's a correction for real gases for the ideal equation. And you see that, you don't have to memorize this, but you see that there's a chart that and it's associated with different gases. And you can do a correction for pressure. So there's a chart there, and then there's also the volume. So what I want to focus on is these two variables are the ones that are affected, pressure and volume. And so what conditions, I ask you, what conditions would cause gas molecules to get closer together? And the reason why that's important, because if they're closer together, they're going to have intermolecular forces. That's what you see in liquids, and that's what you see in solids. And those intermolecular forces dominate their properties. So what conditions would cause, and when you're looking at these variables, well, pressure. If you increase pressure, so high pressure is going to move things closer together, because your pressure, you're pushing in on something. And so these are compressible, right? So the gas molecules in the container, if you put a lot of pressure, they're going to get closer together. So high pressure. You could imagine a low volume. So at low volume, you could push these gas pressures together, these gas molecules together. And what about temperature? Low temperature. So if you decrease the temperature, these molecules are going to be closer together. And then you can have intermolecular forces. So let's do checkpoint problem 10.71. And you do not have to do 10.72 because we're not going to use calculations on these last two sections. So just know how to do your math on the other ones. Okay, which of the following conditions cause deviation from ideal behavior? And it says check all that apply. So we've talked about this, high pressure. So I would choose A, high pressure. So not low pressure. Not high temperature, but low temperature. So that is D, low temperature. And we also said the volume would need to be low volume, and they give you high volume. So A and D are your answers, and that should be correct. And that should summarize what you need to understand and apply in your Chapter 10 gases.